Hey, how's it going, everyone? Welcome to this video. In the last section, we had a look at finding antiderivatives of functions, and we came up with looking at an equation with a constant at the end. So we had a look at if the derivative of y is 2x, finding the antiderivative is going to be x squared plus that constant c. In this video, we're going to have a look at finding the value of that constant for functions when we're finding antiderivatives. To start off with, we'll just take this equation here. When we're talking about that constant, if you remember, we've got a quadratic. That constant just moves the graph of the function up or down. So if we started off with y equals x squared, just simply as it is, it would indicate that we've got a plus 0 at the end. Does the same thing, so it goes through the origin. Whereas if we had x squared plus 3, it would be moving up 3 and going through the y-axis at 3. And take 2 would mean that we go down 2 spots and stop at minus 2. Just remembering from derivatives, when we find the derivative of the turning point, our dy dx, we're actually finding the gradient at 0 would be 0. The gradient at this point, again, would be the same thing. The derivative is going to be 0. Um, that's important for the next page, so keep that in mind. If we had x squared plus c, and we know that it goes through the origin for our first equation, to find what that c value is, we just put in the values for x and y. In this case, it's 0 and 0. So 0 is 0 squared plus c, so therefore c has to be 0. And similarly for this one at 0, 3, we suspect that we get a c value of 3, and just checking that if y is 3, x is 0, plus c is equal to 3. So that's all we're doing. If we're given a point that the equation goes through, we just put x and y for those values. Just a first example, we're starting off with the derivative dy dx is equal to a plus 3x, and it has a stationary point at 2, 5. And if you remember before, stationary points indicate that dy dx at that point 2 is equal to 0. The gradient is 0 at that point. So we can use that information, a plus 3 times, and we're using the point 2. And if we solve for that, a is going to be minus 6. So now I can say minus 6 plus 3x is my derivative function. Now I want to find the original function, in this case y. Remembering we're starting with y, finding the derivative gives us dy dx, and then going backwards we'll end up with y. So finding the antiderivative of minus 6 plus 3x will give us minus 6x plus 3x squared over 2 plus constant c. And we need to use this point here to find what that c value is. So even though it's a stationary point, it is a point that the curve goes through. So using those 2 points, we can say 5 is equal to minus 6 and x, which is 2. Again, 2 plus c, and then we can solve for c as normal. So c is going to be 11. And final step, we say therefore our y equation is going to be minus 6x plus 3x squared over 2 plus 11. Part B, slightly more difficult. We've got the derivative equation is x squared take 4 over 2x squared. We know that f of 4, again remembering f of x is the antiderivative of f dash x. and that's our derivative. So our f of x at 4 is going to be 3. So it's actually given us a point there, which is kind of hidden. So it says when x is 4, my y value is going to be 3. So I can say it's 4, 3 is my point. Eventually, this is what I want to find. I want to find the original function at 1. I've already done it here, but starting with my derivative function, just split up the fraction and simplify, and I'll just finish that off. So x squared we'll have 2 over x squared, and final step, just make that over x squared as a negative indice. So now finding f of x is going to be my antiderivative of f of dash of x, and then I can work that out as half x take adding 1 to the power dividing by the new power plus c, and just tidying up a little bit, two negatives make a positive. Need to work out what my C value is, and I do that by using my point given at the start. So I can use those 2 points. So at 4, we get 3. So 3 is equal to a half. X is now 4. And I solve for C, which gives me a half. So my final, or second last step, f of x is now, keeps going back, a half x plus, I can write that as 2 over x plus a half and then my final step is finding out what happens at 1. So when x is 1, I'll get half plus 2 plus a half, and if we work that out, we get 3. So that's part B of example 3. Next thing I'm going to look at is sketching, or having a look at introduction to sketching. Before I go anywhere, this might be useful because the definitions might be confusing. We're starting with f of x and we find the derivative. That gives us f dash of x. Now finding the antiderivative will give us capital F of x. So just note the difference between them. F dash of x meaning the derivative of the original, capital F of x meaning the antiderivative of the original. Okay, by original it means the equation given. So it just depends what we're interested in. In terms of y, finding the derivative is dy dx, same as f dash of x. Not really a notation for the antiderivative, but we'll just be using capital Fx. So it might be worth jotting down because this next page will make a bit more sense. Just looking at properties of sketching, the x-intercepts of the original function f of x graph identify the x-coordinates of the stationary points of the antiderivative, capital F of x. So again, remembering, starting with this one, we're finding the antiderivative. So it means that the x-intercepts of this one are going to be the stationary points of this one. The nature of any stationary points on the capital F of x is determined by the sign of the graph of f of x as it changes about its x-intercepts. So it's just really talking twice similar examples for both of those. And final one, if the f of x is a polynomial of degree n, then f of x, capital F, will be a polynomial n plus 1. That's just talking about the antiderivative of it. Again, remembering we add 1 to the power, divide by the new power, that's where that comes from. Last example, consider the quadratic function as I've drawn as shown. It's talking us to describe the position and nature of any stationary point on capital F of x, where f of x is equal to f dash of x. So little f of x is really my f dash of x. So the x-intercept on the given graph identifies a stationary point on the capital F of x. So therefore, the graph of capital F of x has a stationary point at x equals 0. So here's my x-intercept. The x-intercept is going to be my stationary point, and in this case, it's at 0. Also, as x increases, the sign of the graph f of x changes positive to 0 to positive about its x-intercept. Alright, so starting from the left, as we go across, we've got all these positive y values here. I don't know what they are. It starts at, well, say 100 and goes down all the way down to 0. As we hit the x-intercept, we have 0. And then we start going back up again into the positives. So we start positive, we stop at 0, and then we go up back to positives. So that indicates that it is a stationary point of inflection at the point where x equals 0. Part B says draw 3 possible graphs for which y equals f capital F of x. So we said we have a stationary point of inflection at x equals 0. So it doesn't really matter, or we don't know what it is, but there's a stationary point somewhere along here, stationary point of inflection, which again, if you remember, looks like that or like that, depending positive or negative. Now it looks like we've got a quadratic to start with. So if we start with a quadratic, finding the antiderivative of it will be a power of 3, meaning a cubic. So it's going to have one of these shapes. First one, simple as we can, just goes through the origin. There's one possible solution. Another one could be this one here where it's below the x-axis, or this one here where it's above. So there's 3 possible solutions. Part C says to obtain the actual rule for f of x. So the graph has a minimum turning point at 0, 0. And so the original function y equals f of x has a minimum turning point at 0, 0. And it contains the point 1, 3. So we know that. We also said that it looks like a quadratic. And if you remember, in turning point forms, we have a x minus h squared plus k, where h and k translate the turning point. Because it has a turning point at 0, 0, I can say y is a x squared. It hasn't been moved up or down. Just determining the value of a, we can use the point 1, 3. So 3 is a times 1 squared. So we can say a is 3. So our f of x is going to be 3x squared. So that's all we need for part C. And part D says, given that capital F of 0 is minus 2, determine the rule for capital F of x and sketch the graph. So I might make a new page, and we need the f of x is equal to 3x squared. So we can find capital F of x by finding the antiderivative of 3x squared. And if we do that, we get 3x cubed, divide by 3, they cancel. F of x is just x squared. And now, just remember, we need that constant. And now we need to find that constant, so we can use the information they gave us. F of 0 is equal to minus 2, or in other words, at 0 we have minus 2. So using those, we find that C is actually just minus 2. And just rewriting the equation, x squared take 2. Sorry, cubed. That should be cubed. X cubed take 2. To be able to sketch it, I need my x-intercepts. Well, if you remember, it had a stationary point of inflection, so we're only going to have one intercept. Probably easier just to solve it for when y is equal to 0. So 0 is x cubed take 2, add 2, and find the cube root of it is going to be our x value. And the final step is just to sketch it. So sketching the graph, I have a x-intercept at positive cube root of 2. So that's my x-intercept, and my y-intercept, I didn't work that out, is when x is equal to 0. So y is just minus 2. Just so happens that we know from past bit of information, the stationary point of inflection is on the x-axis, the y-axis. So we have something that looks like that. So there's my stationary point of inflection at the y-axis, same point for both. So that's 14.3, antiderivative functions and their graphs. Have a go at the questions. Thanks for watching.